MATLAB has many command line functions to create variables, import data, visualize data, and perform computational analysis. You can enter commands by typing in the command window at the MATLAB prompt. For example, typing x equals 5 at the MATLAB prompt will create a variable with the name of x and a value of 5. The command y equals 2 star x creates a variable named y carrying out the calculation 2 times x based on the current value of x. Commands are executed only when the Enter key is pressed. If you need to change a calculation, you need to reissue the command. Y equals 5 times x will create the variable y again, with a new value for y calculated with the current value of x. Oftentimes you might want to go back and execute commands again to carry out the same calculations or perform a similar analysis. All the commands that you enter in the command window are automatically recorded in the command history window. You can use the command history to retrieve past commands at any time, even after you have closed MATLAB. By using the up and down arrows on your keyboard, MATLAB automatically scrolls through all the commands recorded in the command history and automatically enters them in the command window so you don't have to type it again. Store any of the variables you have in the workspace so you can use them in the future. You must explicitly save them in a MATLAB data file by using the File menu, as in the previous chapter, or using the command line function save, followed by the file name. The command save gas prices saves all the variables in the workspace to the file gasprices.mat. If you need to save only some of the variables in the workspace, you can use the function save, followed by the name of the file and a list of the variables you need. The command save French prices France year saves the variables France and year to the file frenchprices.mat. Variables remain in memory until you close MATLAB or until you explicitly delete them. You can delete all the variables in the workspace using the command clear. In addition to the import wizard you explored in Chapter 2, you can also use the command line to load variables saved in a MATLAB data file. The function load, followed by the name of the file, loads all the variables stored in the file to the workspace. Vectors and matrices are an essential part of working with data in MATLAB, as they allow you to store more than one value in a variable. In the previous chapter, you worked with the gas prices dataset, which contains several variables with gas prices of different countries. Most of these variables contain several values. The variable year, for example, contains all of the values of the years in which gas price data was recorded. You can create this vector of values, also known as a one-dimensional array, by entering the values manually inside of square brackets. Entries separated by commas or spaces create a row vector. Entries separated by a semicolon create a column vector. The square brackets are used to concatenate elements into one array. Entering values manually can be time-consuming, and if you are working with very large data sets, it is not practical to enter each value individually. To create equally spaced values, you can use the colon operator. The command year equals 1990 colon 2008 will create a variable year as a vector with a minimum value of 1990 and a maximum value of 2008 in increments of 1. To use a different increment, you can enter a value in between the minimum and maximum values. For example, to create a vector with just the even years, you can specify an increment of 2 with the command even years equals 1990 colon 2 colon 2008. If you don't know the increment size, but you know the number of points that you want in the vector, you can use the function linspace, entering the minimum and maximum values and number of points inside parentheses. The linspace command shown creates the variable with 3 values between 1990 and 2008 inclusive. Both the colon operator and the linspace function create row vectors, but you can reorganize your data as necessary and transform a row to a column and vice versa by using the transpose operator or single quote mark. When working with large vectors, you might not always want to see the result of the commands in the command window. You can suppress this output by typing a semicolon at the end of any command. The semicolon is not required, but it is helpful when working with large data sets. The command linspace with 0, 10, and 1 million without a semicolon at the end will display 1 million values in the command window, which is not practical and can be time-consuming. The command with a semicolon at the end executes the exact same command faster because the semicolon at the end suppresses the result, and the command window doesn't need to display 1 million values. Multiple rows and columns of data into one variable in MATLAB, you can use a matrix. The gas prices dataset you have been exploring contains a table of values with 19 rows and 10 columns that correspond to the gas prices of 10 different countries recorded over 19 years. You can create a similar matrix directly from the command line with the same syntax as the one you used to create a vector. Use the square brackets to concatenate elements into an array, commas or spaces to separate columns, and semicolons to separate rows. MATLAB has a number of matrix creation functions. You create variables. For example, if you need to add noise to the gas prices dataset and need to create a matrix of random numbers, instead of typing a long command and entering data manually, you can use the rand function. The command noise equals rand of 19, 10 creates a matrix of 19 rows and 10 columns of uniformly distributed pseudo-random numbers. Other functions similar to the rand function will allow you to create variables with certain characteristics. The basic syntax for matrix creation functions is variable, equal sign, and a function name followed by 1 or 2 values, which will determine the dimensions of the variable. One value creates a matrix with the same number of rows and columns. And when there are 2 values, the first value refers to the number of rows, and the second value refers to the number of columns. You need to extract or access relevant information from a MATLAB variable, such as the price of gas in Canada in 1990, or all of the prices recorded for a given year. You can use indexing. The most common method of indexing is row, comma, column, in which each element of a variable is designated by a unique row and column number. The gas prices matrix has 19 rows and 11 columns. To extract any value of the matrix, you start by typing the variable name, open parenthesis, row number, comma, column number, and close parenthesis. The command gas prices 1, 3 points to the first row, third column of the variable gas prices. Keep in mind that row and column indices in MATLAB always begin with 1. The first row is row number 1, and the first column is column number 1. As always, you can save the result to a variable using the equal sign. Canada price 1990 equals gas prices 1, 3 will assign the value of the first row, third column of gas prices to the variable Canada price 1990. To extract more than one value of a matrix, such as all of the prices recorded in the year 2000, or the first and last prices recorded for Japan, you can use vectors as the row and column indices. 1 and 19 inside of square brackets creates a vector with these values. You can use this vector as the row index and extract the first and 19th rows. The command shown extracts rows 1 and 19 of column 7 of the variable gas prices. You can also reference a range of rows or columns in a variable using the colon notation. 1, 10 creates a vector with the values 1 through 10. When used as the row index in the command German prices 90s equals gas prices 1, 10, 5, it will extract rows 1 through 10 of the fifth column of gas prices. To extract a complete row or a complete column, you can use the colon operator on its own. For example, UK equals gas prices : 10 extracts all the rows of the 10th column and saves all the prices for the UK as a separate variable. If you gather data of the gas prices from 1980 to 1989 and want to combine the data with the original gas prices matrix, which contains the prices from 1990 to 2008, you can use concatenation to combine two arrays together. In the previous lessons, you have learned that you can concatenate several values using square brackets. Commas or spaces are used to position elements side by side, and semicolons are used to position the elements vertically. You can also concatenate vectors or matrices using the same principles. The matrix gas prices 80s can be combined with the original gas prices matrix with the command open square bracket gas prices 80s semicolon gas prices close square bracket. Keep in mind that when you are concatenating arrays vertically with a semicolon, all the arrays need to have the same number of columns. Otherwise, MATLAB will return an error. In the same way, when you are concatenating arrays horizontally with a comma or space, all arrays must have the same number of rows. If you are going to be performing analysis on the gas prices of different regions, you might consider combining individual vectors with the data of specific countries into one variable. The command America's prices equals open square bracket Canada, Mexico, US, close square bracket will combine the prices of Canada, the US, and Mexico into one variable. The variables Canada, Mexico, and US need to have the same number of rows, or MATLAB will return an error. When you don't have all of the data, you can always complete a matrix with NaN to make sure that all variables have consistent dimensions. In addition to working with numerical values, MATLAB variables can store other types of information, like text, so you can store a name, a label, or a description, and use it in many different ways, like the title of a graph or a file name. To create a variable that stores text, you need to enclose characters in single quotation marks. The class of the variable description is no longer double. It is of class char, which indicates the variable type is a character array, and it can save more than just alphanumeric characters, such as commas and parentheses. The rules for indexing, assignment, and concatenation you have applied in the previous sections with numeric arrays are all still valid with character arrays. Description is an array of 1 row and 40 columns. You can index into the variable using row-column indexing and extract the currency by using the command price currency equals description 1,26:39, which extracts the first row, columns 26 through 39 of the variable description. Character arrays can also be used in functions as inputs. The command save, explained earlier, can be used with the command syntax save, space, and a file name, but it can also be called using a function syntax, with the file name inside parentheses. When using the function syntax, the file name must be a string. The command save of quotes gaspricesdata.mat saves all the variables in the workspace to the file gaspricesdata.mat. Note that the file name is a string because it is enclosed in single quotation marks. In contrast, the command save of gaspricesdata.mat without the single quotes will attempt to pass the value stored in a variable called gaspricesdata into save, which will return an error. You can assign a literal string to a variable and use the variable of class char as the input of the function. Save of new file name will pass the value of the variable new file name to the function and save the variables in the workspace to the file updateddata.mat.
Two vectors of the same length can be plotted against each other with the plot function. Plot xy plots each element of x on the horizontal axis against the corresponding value of y on the vertical axis. For variables year and France, the command plot year France plots the France data against the year data. Note that the plot shows each element of year in the horizontal axis against the corresponding element of the gas prices of France on the vertical axis. If only a single input vector is passed to plot, the vector is plotted on the vertical axis. Plot Germany plots the values of the gas prices of Germany against the vector index values in the horizontal axis. The value 2.65 of vector Germany is plotted on the vertical axis against the value index 1 on the horizontal axis. 2.9 is plotted against index value 2. 3.27 is plotted against index value 3, and so on until the last value of 7.75 of the gas prices of Germany is plotted against index 19. By default, the MATLAB plot command displays a blue solid line with no marker, but the plot function accepts an optional third argument that allows you to specify the basic properties of the plot appearance, such as line style, line color, and marker style. These options are specified inside single quotes as a string that can have 1, 2, or 3 parts. The command plot year Mexico R plots the Mexico gas prices in red, and the command plot with a string of R, O, and 2 dashes plots the line series as a dashed red line with circle markers. Note that the codes can be combined in any order. So the string with 2 dashes, O, and R will also plot a dashed red line with circle markers. Here's a list of all the codes you can use inside the plot command to change its default appearance. You may select any combination from the list and observe the results. You can add text to your plots using annotation functions, such as title, X-label, Y-label, and legend. All of these functions take a string input. Title, followed by the string, and prices to the top of the plot. X-label, with German prices as a string, labels the X-axis. Y-label, Mexican prices, adds this text to the Y-axis. And legend, Ger versus Mex, adds a legend to identify the line series. By default, the legend is positioned in the top right corner of the plot. The legend function also accepts additional arguments, such as location followed by a string, which allows you to specify a different spot for the legend. Legend, Ger versus Mex, location, south, puts the legend on the bottom of the plot. For a complete list of the location options, look at the documentation by typing doc legend.
You can start your analysis of the gas price dataset by performing some currency exchange operations on the data. Note that the prices matrix is 19 rows and 10 columns. Each column represents the gas price data for a different country, and each row represents an observation of the data at a given year. Currently, all of the prices are in US dollars. Given the currency exchange rate, you can convert the prices matrix from US dollars to euros. To do this, you can multiply the prices matrix by the scalar currency exchange rate. As with vectors, when you multiply a matrix by a scalar, each element of the matrix is multiplied by the scalar value. This results in a new matrix where all of the gas price data is in euros. Instead of converting the gas price data to one single currency, you could use different exchange rates for each column of data to convert the prices to their native currency. Currency exchange rates also vary from year to year, so ideally you would multiply each element of the prices matrix with the currency exchange rate that is appropriate given the native currency and year the observation was made. The matrix on the right represents the currency exchange rate for each element of the prices data. Here, to do the conversion correctly, you need to multiply the elements of the prices matrix by the corresponding elements of the currency exchange rate matrix. To do this, you cannot use the star operator, as that will cause an error. This is because when multiplying two arrays, MATLAB uses mathematical matrix multiplication, not element-wise multiplication. Instead, you should use element-wise multiplication. To do this, you must use the dot star operator. The dot star operator causes each element of the first matrix to be multiplied by the corresponding element of the second matrix. This results in the correct currency conversion. Note that to use element-wise multiplication, two matrices must have the same dimension. If the matrices are not the same dimensions, then MATLAB will throw an error. There are other element-wise operators besides dot star, such as element-wise division and element-wise exponentiation. For instance, you could find the ratio of two sets of gas price data by dividing them using element-wise division. This causes each element of one dataset to be divided by the corresponding element of the other dataset. Also, Don't forget that addition and subtraction are always element-wise operations. Though it was not directly useful in the currency exchange example, mathematical matrix multiplication is actually a very powerful tool. For instance, you can use it to obtain more sophisticated statistics, like finding an average of all gas prices over time, weighted according to the relative populations of the 10 countries. Here, the values in the R variable represent the corresponding country's population as a percentage of the total population. Before attempting to calculate the weighted average, you should have a firm understanding of matrix multiplication. Remember that, in mathematics, to multiply two matrices together, the number of columns of the first matrix must equal the number of rows of the second matrix. Then, for the multiplication, each element of a row of the first matrix is multiplied by the corresponding element of a column of the second matrix. The resulting products are then summed together to produce one element of the final result. This is then carried out over all rows and columns of the two matrices. The equation shown is the equation for finding the weighted average of the gas price data over time, where each weight is that country's percentage of the total population over all countries. This equation can then be cast as a matrix equation, where the number of rows of the population vector is equal to the number of columns of the prices matrix, one for each country. By multiplying these two arrays together, you are left with the weighted average of the gas price data over time. You can calculate the weighted average in MATLAB by first defining the population vector rpop. Note that the values for rpop are all less than 1, since each value indicates the fractional value of a single country's population when compared to the total population. Once the population vector is created, you can use mathematical matrix multiplication to calculate the weighted average. You have seen that by grouping data into a matrix, you can perform sophisticated arithmetic on the data to manipulate it as a group. Additionally, you can use data grouped into a matrix in many MATLAB functions to perform common analysis tasks. In this section, you will round the prices data to the nearest integer and find the average of each individual country's gas price data. To accomplish these tasks, you can generally think of matrix data in one of two ways, either as a single mathematical entity or as a collection of vectors. For instance, many mathematical functions, such as the round function, will treat a matrix as a single mathematical entity and operate on each element individually. This behavior makes sense for any function that is typically applied to a scalar number, such as round. This is the same behavior as was seen with vectors. Thus, by using the round function on the prices matrix, you rounded all of the gas price data in a single function call. Note that many functions, such as sine, log, etc., all behave as mathematical functions. In contrast, many statistical functions, such as the mean function, will treat a matrix of data as a collection of vectors. Therefore, when you take the mean of a matrix, the mean function is applied to each column individually. This makes sense for many functions which are typically applied to a set of data, such as mean. Thus, by using the mean function on the prices matrix, you found the mean of each of the gas price data vectors with a single function call. Note that many functions, such as standard deviation, sum, etc., all behave as statistical functions. When dealing with tables of data, it is often useful to visually compare the data to observe values, trends, and outliers. For this, you can plot the individual gas price data on the same axes. How could you plot all of the columns of the prices matrix on a single set of axes? Fortunately, two-dimensional plotting functions such as bar, plot, stem, and so on behave in the same manner as statistical functions when dealing with matrices. The columns are assumed to be independent variables. Hence, when you plot the prices matrix using the plot function, each column of the matrix is created as a separate line plot. By default, the colors of the lines cycle through a standard sequence of colors. Here, the data is a bit overwhelming. Perhaps instead you can focus on only the European gas price data, which is located in columns 3, 4, and 5. To do this, you can use indexing to create a matrix that contains the columns of the European gas price data. Then you can plot this data using the newly created matrix. Notice that the gas price data of the European countries is very highly correlated, as you might expect given their geographical proximity. You can even add a legend for additional visual clarity. For multiple plots, you can pass a comma-separated list of strings to the legend function to name the plots in order.